So my research area is on foundations for autonomy. So this area has had a long history, and my background in computer science has always been in computer science, but in computer science, it's in an area called formal methods. And essentially, formal methods is an area where it's been the application of techniques from multiple areas, but mostly from logic, automated reasoning, uh, to try and have computers prove properties of programs. So my whole interest in formal methods started when I was an undergraduate student. And one of the things you learn as an undergraduate student is there are certain problems that computers cannot solve. Um, it's almost like nothing can travel faster than the speed of light, right? And it's a truth that one thinks that any problem that you could think about, you could apply a computer to solve it. I mean, no, forget about like human problems, but at least any technical problem involving computers, computers should be able to solve it, right? You should be able to calculate anything that you can describe, right? And it was a mind bending theorem, and it's due to the work of Turing. I hope many of you know about this or remember this back from your undergraduate days, that you cannot prove certain things are not computable. So, and one of the things that's not computable is, suppose I'm given a program in C, C++, think of your favorite programming language, and I'm asked a very simple question: does this program terminate? So is it going to terminate, finish, or am I going to have to press Control C because it's going to run forever? Or so the opposite of terminate is it's going to run forever, right? And in fact, you can make it even simpler. There is a program, it's already gotten an input. So then my question is it going to run forever or is it going to terminate? And one of the fundamental theorems in computer science is you cannot use a computer to tell you whether a program, even on a given input, is going to terminate. And this is called the halting problem. And I was really interested in, so looking at the halting problem, then I started thinking about like, maybe, couldn't we just do this? Like, couldn't we look at a loop in a program and say, is this loop going to terminate or is this loop going to run forever? And that was my entry into formal methods, thinking about the problem of, given a program, how do you establish that the program terminates? And then I learned about the wonderful world of theorem provers. So theorem provers are essentially one of the main tools we use in formal methods, and these are they could be of many sizes and shapes. What a theorem prover is essentially it allows you to prove mathematical statements. And one of the mathematical statements you could make is this program is correct. And theorem provers can help you prove theorems. There are many theorem provers around. Actually, one of the famous historical ones is from France. It's called POC. It's a theorem prover. Another one that you may have heard about recently is called Lean, which is a theorem prover jointly from Microsoft Research and CMU. And Lean has been in the news a lot recently because mathematicians are actually starting to use Lean to prove theorems. So Lean has become powerful enough that number theorists like Terence Tao recently blogged about how he was using Lean to check one of his proofs, and he found a mistake in his proof, and he was working with Lean to fix his proofs. And theorem provers are also called proof assistants. So what they do is, think of you trying to prove a mathematical theorem, and think of an engine that anytime you try to make a statement, it will challenge you to prove it. And until you can satisfy the theorem prover, you haven't proven anything. So it's a way of working inside logic to try and establish a statement in mathematics formally, like a statement like, for all n greater than equal to 1, for all a greater than equal to 2, b greater than equal to 2, c greater than equal to 2. a to the n plus b to the n is not equal to c to the power n. So this is an example of a statement in logic. I mean, this should be n greater than equal to 3. So what it says is what is called Fermat's last theorem, right? So you could write statements in mathematics in logic, and a theorem prover is a step-by-step guide that you can guide to help you go from a statement like this to a proof. I don't want to get too technical, but this is the kind of work that we do in formal methods. In formal methods, we try and establish foundations by which you can express statements and guide them to a proof. A lot of times there is some interesting AI magic involved, and this has also been in the news recently. And AI is usually involved in like giving you this guiding hand of like which tactic would you use to prove something. Just like a human has an intuition of how to go about proving something, AI can try and add to that intuition, but fundamentally it's a human process of starting from a statement and going to a proof. And what a theorem prover makes sure is you cannot do a wrong step. You cannot make a mistake in your proof. So whatever moves you make are going to be mathematically valid. So this is standard technology right now, and there's a lot of examples. And my research kind of takes off from this kind of a background area called formal methods. We use logic and we use foundations to describe what are computer systems, what are models of computer systems, what does correctness of computer systems mean. Termination, for example, is just one kind of correctness. And so there is a lot of technology called theorem proving, and we use that to prove. So this is the overall general the world as it is. And my research applies all of this technology to talk about autonomous systems. But before we go into autonomous systems, any questions on this area called formal methods? I mean, I gave you a very, very brief description. If you entered graduate school, it's probably a couple of courses that we offer, and then reading a bunch of papers and getting some hands-on knowledge. But any questions so far? Okay, no questions. All right. I guess I will keep going. So then let's get to the second part, which is autonomy. So what is autonomy, right? So autonomy comes from, I guess it comes from auto, which means self. And the root nomi typically refers to government, right? So it's like self-governing systems. And autonomous systems have been around for a long time, right? And these are kind of systems that try and work without much of human intervention, right? So typically in an autonomous system, you give the system some goals, and these could be high-level goals, and the system goes ahead and tries to achieve that goal. Right. So autonomous agents, for example, you could have an autonomous agent and you could tell that agent, like, go book me a ticket, and make sure that the cost of the ticket doesn't exceed $300, and you give it some requirements, and the system then goes on the internet and tries to purchase a ticket from A to B, wherever you would like to go, whenever you would like to go, tries to make sure that the cost is within budget, that the time constraints are within what you say. It books the ticket and comes back and says, hey, I did it, I successfully, here's your ticket. Or it says, okay, I tried, and this is the best I can do instead, right? So an autonomous agent is a decision-making agent, okay? And one of the main things about autonomous agents is they make decisions, and they are essentially working in an uncertain world. So the world in which these autonomous agents operate is pretty much uncertain. So when you talk about booking a ticket, it's not all that uncertain, but still you could have certain uncertainties, and the agent needs to have some knowledge of the world to be able to do a task like this. Okay, and this is classic you would study problems like this in AI. But let me give you a more real world example of an autonomous agent. And this could be an example, could be artificial pancreas, which is a system we study in our group. And this kind of a system is useful for people with type 1 diabetes. And the idea here is people with type 1 diabetes cannot make a very essential hormone in their body called insulin. So they are unable to make insulin. And because they cannot make insulin, their blood glucose levels are not easy to control. So typically their blood glucose levels will be elevated. Insulin is a hormone that brings blood glucose levels down. And so because their pancreas, which is the organ in the body that makes insulin, doesn't function to make insulin, there is an external insulin delivery system called an insulin pump. And the pump delivers insulin to the human body. And there is a sensor that senses the glucose. So this would be a simple example of an autonomous system that is constantly sensing the blood glucose levels. And based on the blood glucose levels, there is the algorithm that decides on how much insulin should be injected into the human body to keep the blood glucose levels within the normal range, or what's called the euglycemic range. Okay, and so such a system works 24/7. There is a decision-making algorithm. So it is going to make decisions. Okay, so it's an autonomous system. It makes decisions. And it works inside an uncertain world because there is a couple of sources of uncertainty, or there's a lot of sources of uncertainty. The two main sources can be classified as physiology. So people's physiology is inherently variable. Maybe you're not feeling so great today. Maybe you have a fever. Maybe you physically exerted yourself. Maybe you have muscle ache. So there's a lot of different physiological conditions that people can be in. And that determines how the blood glucose level is going to go. So that's a source of uncertainty, because this device only has control over insulin. It has no control over, it doesn't deliver Tylenol to you, or it doesn't cheer you up when you're feeling low, right? So it's not going to do all of those things. So physiology is completely out of our control. The other thing that's out of your control as a device is human behavior, especially human behavior around meals and exercise, because what you eat and how you exercise is going to affect how much insulin you need. So this kind of a system is making decisions under uncertainty. All right. In fact, it's making decisions under a lot of uncertainty. And the last bit that I want to emphasize the difference between booking a ticket and controlling blood glucose levels. Maybe I'll ask you for it, since no one's been responding to me so far. What's the big difference between booking an air ticket and controlling blood glucose levels?
Nobody's going to die if you buy the wrong ticket.
Yes, that's it. No one's going to die if you buy the wrong ticket. I mean, you're going to be out of some cash. Okay, you might be annoyed. You might actually take a hit on it, but no one's going to die. Whereas here, if this device gives you too much insulin, if it makes the wrong decision, then people are going to die. So there is a notion here that characterizes the systems we study. They are safety critical, which means that they make decisions that cause life or death, or worst case, severe damage in case of malfunction. So you want to make sure that this kind of a system is really, really safe. I mean, safe beyond what you would normally care about. Let me give you an example. Safety is going to be a very difficult concern, right? As an example, like one anecdote I've heard is what happened is two people with similar system were walking close to each other, and unfortunately, one of the person's pump, and these were doing some kind of Bluetooth communication paired with another person's sensor. So one of the person's sensor paired with another person's pump. So imagine you are one of the persons is like a 6'4", 200-pound man, and the other person's 5'2", 80-pound preteen. The amount of insulin that one person requires would be a death dose for another person. Like it would kill the other person. Like the 200-pound man would need a lot more insulin because of body mass and imagine one person's sensor just ended up pairing with another person's pump. What is going to happen is disaster.
Well, that's not really a formal methods problem though, right? That's an engineering problem, isn't it?
Absolutely, right? So that is an engineering problem, right? So there are a ton of engineering problems, right? Absolutely, you're absolutely right? And so the formal methods problem is really to understand whether this algorithm will keep you safe, assuming that all these engineering problems are solved, right? Then the formal methods problem is to say, is this algorithm appropriate? Is it reacting appropriately? And I wanted to show you that formal methods is just one aspect of safety, but it's the aspect of safety that we care about. Whereas you really have to engineer safety in a lot of different ways. But those kinds of safety, assuming they are solved, then you are left with the formal methods safety. Okay, and here I'm really asking, is this algorithm correct? In a sense, if you take this algorithm and run it, will it keep the person safe? Will it make sure that the person never receives too much insulin or too little insulin, right? So what you have is an interesting question here, but questions like this are inherently difficult to answer because it's not just a question of this algorithm or software. So it's not just about the correctness of the software, because the correctness of the software in isolation itself is a problem that formal methods cares about. But in this case, it's more than the correctness of software. It's the correctness of the software that is running in conjunction with a physical environment. So most of the problems we solve have a software system that's essentially working with a physical environment, or I'm just going to call it physics, but it's actually, in this case, it's biology, or physiology, like human physiology and human behavior. But you have a piece of software that's working with a physical environment, and this is called a sense, compute, actuate loop. And so really, you cannot talk about correctness in isolation. If you just focus on the software, you cannot really talk about whether it's correct or wrong. You could, but those are issues of correctness, like does it have a null pointer? Does it have a null pointer dereference? You could talk about security properties. Is it authenticating the device that it is going to send commands to? The software is going to send a command to the pump to go and deliver. One of the issues I mentioned, where someone else's pump is delivering insulin meant for another person, is also a failure of authentication, because you should be authenticating that you're sending commands to the right pump. So these are all software only issues, right? These are issues that are primarily inside the software. The question that I'm talking about is a closed loop issue, where I'm really talking about, given a piece of software, and usually it's very simple software. These algorithms are not very complicated. They are usually like, if the blood glucose level is higher than this level, give them this much insulin. But if you are given them this much insulin for a while, then back off a little bit. And then, so there is like a few like rules, if then else kind of rules. And the software is usually a big set of if then else statements, but it often gets complicated. These things take on a life of their own, right? But then it's the algorithm in conjunction with how blood glucose levels evolve. And for this, we need models. So we need models of the world around us. And typically, the kinds of models we use are called ordinary differential equation models. We have also tried using neural network models. I'll talk a little bit about that, about some of the dangers of doing that. And there is a ton of other ways you can do it. There are something called partial differential equations, though I don't study it. No one I know studies it. They are too complicated for our purposes. Typically, in a blood glucose level situation, you would be looking at ordinary differential equation models. And these ordinary differential equation models look at insulin as an input, And typically they can have other inputs like meal, carbohydrates, and then they will predict how the blood glucose levels evolve over time. So these models, then you combine them with with your software, or at least the algorithm. You could use some kind of a description of the algorithm, and you create a closed loop. And there are some external inputs to this closed loop. And then you study this closed loop and you say, does this have the properties that I want? Right? That are desirable. And I'll talk about what is desirable in a second. But typically in a blood glucose level setting, you would say, okay, if my blood glucose level is between 70 and 180 mg per DL, if I'm starting from here, how far up do I need before I'm able to come back down, right? So typically you would want to establish that you never go above 300 mg per DL, which has a clinical significance. It's the level at which your blood starts having ketones. So you want to have a property saying, if I start from somewhere in this range, I will not go over 300 mg per DL, even in the worst case. I want to place a bound on how far ahead I go. The other kind of property is, if I go over 180 mg per DL, which is taken as the upper end of normal, I want to put a bound on the time I spend in the hyperglycemic region. Okay. And the point here is we do this kind of, we study these kinds of problems. We have we try and place software, or at least descriptions of algorithms. I should call them algorithms, because when I think about software, typically in a software system like this, you have device drivers, you have the way you are sending commands to a physical interface, the way you are receiving data from your glucose sensor, and how do you decode that data, the authentication mechanisms, all of that is part of software. An algorithm is just the pure guts of it. Like, you just say, okay, if the blood glucose levels more than 80, back off insulin. If it is below 80 and it is rising, then back off insulin. If it's been below 80 for a while, then start insulin. So there are all these rules, and so you would have a rule-based system that looks at the history, looks at the current glucose, and then gives a decision on how much insulin to inject. It's just a simple rule-based algorithm, if you will. And you put that rule-based algorithm in conjunction with a differential equation model. And then you talk about proving bounds on a system like this. Okay. I'm not going to go into the details of how we do that, but this is kind of the real guts of our work. I'll give you some idea how we do that, but yeah, go ahead.
I'm kind of interested in hearing a little bit about, like, a person, a living human being isn't really a closed system with defined parameters, right? They evolve over time. So what's the systems? What are the feedback systems that are used in order to fine tune the algorithms?
Not much at this point, because they are considered too dangerous to fine tune. And not enough is known about that. And so right now, the devices that are on the market are what are called first generation devices. They operate very, very simple feedback strategies. They are called PID loops, if you know a little bit of control theory. They are extremely simple controls. That's what FDA has approved. Now, the more complicated ones are coming. Right now, they say that these systems are adaptive, like they adapt to how people evolve over time. But FDA does not like too much of that going on, because all of that means that is you lose control, like you lose predictability. And FDA wants these devices to remain predictable. So the medical device world, there is a lot of go it slow, right? Safety is very important. But right,
yeah,
I mean,
there's a fundamental conflict in that approach, right? I mean, part of that,
yeah,
sure, you want to have some known parts, but on the other hand, like, the way humans are is to a large degree variable.
yeah.
And maybe insulin pumps is not a good example of where you would want a probabilistic approach, but I presume that there are other systems in which a probabilistic approach would be valuable.
Exactly. So yes. So I'll talk a little bit about that. We do some work on probabilistic systems as well. The theory of how to do this for probabilistic systems is little bit much more complicated than how to do it for just differential, like dynamical systems with software. By the way, these systems have a name. It's a very boring name. We call them hybrid systems. Let me unlock my. These are called hybrid systems. We've been studying them for a long time. These are systems where there is some switching going on along with a continuous evolution of states. And we have done a lot of work. So my group operates on two layers. So there is the theory, and then there is the applications. And I myself operate on two levels. I am personally very, very interested in a few problems. So in terms of theory, we look at the technical area in which this belongs to is called reachability analysis for hybrid systems. So this is I mean, it's highly technical. I don't want to get deeper into it. But it's been really exciting. I've been working on this since the last 20 years. We've been working on algorithms for doing reachability analysis. We have tools for doing reachability analysis that people have. I have a former student who has been working on a tool, and he's kind of made it his life's work to develop and maintain that tool. He's faculty at University of New Mexico. And a lot of people use his tools. He maintains this tool called Flowstar, which is the kind of tool we use for specifying a system and verifying that. Application would be artificial pancreas, for which I actually work with people in our medical school. We have a center called the Barbara Davis Center for Type 1 Diabetes. So we work with people there. We actually work with device manufacturers on their actual designs. We try to verify them. So we've been very active in this space. We have an NIH grant going on that tries to address some of Paul's questions about how can you adapt these devices to human behavior and changes in physiology? How can these devices function better with people? And so I'm working with human factors people to understand better, like how people make decisions and how those decisions can be made in a good way. How can we keep them safe? And so on. So there is a lot of interesting questions that we answer in this, and that goes like way beyond just safety. The artificial pancreas area just took on a life of its own. And so there's a lot of interesting research on the next generation devices, which are going to do some of what you want to do, Paul. And we are talking about how can we prove safety? How can we give assurance that these devices are not accidentally going to kill? Like, let me give you an example, right? Let's say the device is learning from your daily meal patterns, and it learns that you like to eat at, not you and anyone here, but a person likes to eat at noon every day. Okay, so then the device can say, gee, I can optimize this person's habits by knowing that they eat at 12. They've eaten at 12 noon every day for the past 2 months. So I could optimize for it, and by giving them a bolus and like in advance, knowing that they will eat at 12 and everything will be fine. I'll give them a bolus at 11:40, and I know they will eat at 12. And let's say one day the person's going to eat at 12, and let's say their coworker finds them in the lobby and engages them in a conversation, even though they wanted to eat at 12. It's now 12:30 and they have not yet eaten. But at 11:40, the device made a decision that, hey, this person's going to eat at 12. I'm going to bolus them with insulin. And they haven't eaten till 12:30. And so that's a classic case of when they will get the hypoglycemia, right? They will start shivering and they will have to, worst case, go to a hospital, right? So there is danger in learning patterns, because the day a person breaks a pattern is the day the device makes a wrong decision. And so then there's questions of like, how much authority can the device take on? Like how much risk does it take on in making a decision on behalf of a person, right? So these are all questions we are engaging in at this point, right? So people who are manufacturing devices are interested in how far they can push the envelope while still maintaining safety. But safety is paramount. You don't want to find like accidentally kill someone through these kinds of devices. So FDA restricts these devices on how much insulin they can give at one point in time. It cannot be given, like it cannot give more than this fraction of the insulin that you need. The remainder has to be the person's own decision to give themselves the insulin. So there's a lot of restrictions around devices like this. That's one application. The other application is we work with our colleagues in robotics. Especially we have had a long collaboration with Chris Heckman's group, and Chris Heckman works on many projects, including self-driving cars. So he has his model cars that he basically runs around tracks. So we work on driving algorithms, which are very similar. These are algorithms that control a vehicle, and we want to prove that, you know, when you want to drive an aggressive trajectory, not your standard like simple turns, but when you want to make aggressive turns at high speeds, question is, could we model that? Could we provide like safe controllers for doing these kinds of turns? And so these are examples of where we work with Chris. And I mean, so this is an example. Another problem is called the stability problem, which is again in the theory side. We also work on probabilistic systems, exactly like Paul mentioned. You know, these are very, very important to model uncertainty, like actually model stochasticity in these systems. So we do that. I mean, the theory gets very interesting. I mean, I have students who work on the theory. I have students who work on the actual systems. Recently, we started looking at machine learning, especially machine learning for the artificial pancreas. We started thinking about, you know, a lot of people are really interested in taking away a differential equation and instead plugging in a neural network. And the network is very simple. All it does is it takes in predictions of people's blood glucose, past blood glucose levels, like whatever their blood glucose levels has been in the past, tries to forecast their blood glucose levels out into the future. This kind of a forecast can be personalized forecast. Like I could make a forecast model for me based on my data from the last 20 days, or I could make a forecast model for you based on your data. Right? It's personalized. It's based on your physiology. That's the advertisement, right? But at the same time, when we started doing it with neural networks, we found that this was terribly dangerous. And this was PhD work from my former student, Taisa Kushner. And what we found was neural networks are extremely bad at forecasting in the following sense. So we could give past blood glucose data and ask it to predict future blood glucose data. Let's say 2 hours out into the future, we could give it past blood glucose, past insulin, and ask it to predict the future. And what we found is on the training data, the training error, like very simple neural networks will do it, like 2 layers, 64 neurons a layer, or let's say ReLU units. The training data performance is excellent. You get within like 5 mg per dl of the actual blood glucose values. And one would think that this is great. This is very promising, except as formal methods people, we wanted to know what is happening inside this neural network. It's a black box. It's just a bunch of circles and arrows, and what is happening. And we were horrified to actually find out that this neural network had learned something horribly bad, which is it learned that when you give a person more insulin, their blood glucose level goes up as opposed to going down. So in other words, it fits the training data perfectly. I mean, the performance on the test data is a more complicated story. But what it learns is it's the wrong fact is what it learns. It's imagine you try to train a neural network as a surrogate model for your car. So, okay, you press your accelerator, your car's supposed to speed up. You press your brakes, your car's supposed to slow down. But imagine your neural network actually learned the reverse. Like you press your brakes, your car speeds up, and you press your accelerator, your car slows down, but still fits the training data really well. Like, how is that even possible, right? And we were scratching our heads until we found out the reason. The reason is in all the clinical data that we trained this model on. As it happens, anytime a person gets a large insulin bolus, they also eat a meal. So the point here is you eat a meal, you get some insulin to go with the meal, and then the blood glucose level goes up. But that's due to the meal, not due to the insulin. But then the insulin kicks in and the blood glucose level comes back down. Okay. Now the poor neural network doesn't really know which one of these two, the insulin or the meal, is the causal factor for the blood glucose level to go up. And meal data is never recorded, right? Meal data, people do a very poor job of recording meals, so you never get meal data. So then all the neural network is left to conclude is every time you see insulin, you see a spike in the blood glucose levels. So who caused the blood glucose levels to go up? The insulin, right? So you get, and of course, the amount of insulin is always proportional to the amount of meal. So it all works out. You get very nice fits. 2 hours out, you're able to still predict the blood glucose levels very well, but you have done it for exactly the wrong reason. And we found that this
is there something you could do, like with time shifting, where you could say, we know that it takes some amount of time to metabolize insulin and start having an effect, and so we're not going to actually feed you the insulin reading of right now, but instead we're going to feed you the current the current blood sugar rating and the insulin from, I don't know, 20 minutes, something like that.
Yeah, so something like that could be done. The easier thing to do is to actually enforce that there is a monotone relationship. And in fact, this is typically called inverse monotone relationship. Inverse monotone relationship typically tells you that when some input goes up, the output correspondingly must go down in response to that. So you could actually force neural networks to respect a form of inverse monotonicity when you learn. This is kind of side information. And so when we put this side information in, the problem gets fixed. But this kind of leads you to like the interesting fact that machine learning is extremely successful with a caveat, right? When you really care about safety, when you really care about correctness, you have to ask questions like, is it really learning the concept, or has it just learned to fit the data, right? And if you don't ask questions like that,
that's the problem of having parameters that aren't exposed to the model, right? And
exactly.
If you know, you have to be aware of what parameters there might be that the model isn't exposed to.
Absolutely. Right. So there's a ton of problems happening here. It's a problem of the machine learning kind of models itself, like neural networks. There's no way of incorporating background data into them. They are just black boxes. The second problem is the data itself often has biases. There are like, and this is a classic problem of distribution shift or data distribution shift, right? The data under which you train networks is often not the data under which you try to use them. And so often generalization is very poor. There's so many problems here, but one of the things that I've used formal methods is to help us find questions like this for which we can get answers, right? So the goal is, how do you interrogate a neural network and find out what kind of knowledge has it assimilated inside it? How do you find out this kind of facts, right? How do you take neural networks and boil them? So in some sense, I'm really interested in getting machine learning right in this sense, right? Like there are domains where you want to learn the concept, you want to learn models, but you want to learn models which are respecting some physical laws or some biological facts, and we call this conformance-based learning. And we've been working on quite a few ways to detect problems like this in neural network models, or even be able to debug. But it's kind of it goes like domain by domain. There's no general thing that we have found, but we are still working on looking at data and trying to predict that problems like this are going to be inherent if you try to use this data.
So in a problem like this, right, could you start with the basis of like general biology, where you would take a large sample set and kind of use that to generate a general model, and then to refine the feature files based on an individual, so that you used to have a pretty good starting place, and then a refinement off of that? Has that been looked at?
That's a way to do it, but we don't understand neural network enough to I mean, one way, what you're talking about is a way of like creating a prior. In a sense, you want to start with a good baseline model that already has some of the facts into it. and sometimes, these kinds of networks transfer very well over to the data, like from the general data to the data that you want to learn, right? But in many cases, not. Like in clinical examples, the data that you have is the data that you have. Like, you're not going to get any more data or any background data. But there are obviously many approaches to this problem, right? And one of my students is starting to look into how to solve this outside of the artificial pancreas world. Taisa's thesis was just looking at blood glucose level models and how to get that right to the best of our ability. Now we are really interested in the more general question of how do we learn physics models, especially when you have these dynamic models where the output of the model goes back as the input for the next time step. You really want to make sure that your model has some desirable properties. Otherwise, it's not going to model physical phenomena very well. So we are really interested in like background knowledge, like how do you ground up give the right background for a model. Like in physics models, you want conservation of energy. If you're modeling charge, you want conservation of charge. If in chemical reaction networks, you want conservation of mass. Like, there are all these physical properties that are sacrosanct, and you don't want models violating these physical properties. Like, I just came back from a workshop where we were talking about climate science, and they were talking about, when we model weather phenomena, we have all these cells, and we want to make sure that there's conservation of mass, conservation of momentum globally across the entire domain, like when we are doing wind modeling or something like that. So people care about this in physics-based models, and you really want to understand how to do it how to build models that respect physics laws. And so that's an example of a domain where I'm super interested. There's a lot of interesting new frontiers for, like, neural networks are going to be called on to model ice sheets, or neural networks are going to be called on to predict how hurricanes are going to blow, right? So people are very interested in this, but if those networks don't respect the physics of the problem, then they are going to give you wild predictions that you really can't trust. So I think formal methods has a role to play there as well. So we have quite a group here of people other than me who do this. And so, and we have quite a few projects as well. I'm not going to tell you all of them. We have started working on with people in cognitive science on looking at humans and their interactions with machines. How do we model human decision making? The same way, like, could you build mathematical models of how people make decisions? What kind of decisions would they make? How do you incorporate them in your design to design for safety, or how do you incorporate that in a design for, like, understanding whether your system will have a vulnerability? So there are lots of very interesting problems that come up when you take formal methods and put it in the physical world.
Is that
all right?
like,
I'll stop there. Take some questions.
Is that like looking at the general problem of the hallucinations that we see in large language models, where they give a very convincing yet wrong answer?
Yeah, I mean, yes, for the most part, for my work, I avoid machine learning unless I really avoid. I mean, some of my students work with large language models, but I personally don't like to mix metaphors. And so for me, there is a role for large language models. Like, one nice role for large language models is to make verification tools usable. For example, you could, people are thinking about interfaces to theorem provers using large language models. But then there is a safety layer that makes sure that you're not going to prove something wrong. It's just there so people can use natural language text to interact with the theorem prover. The large language model translates natural language into mathematics. Or people are using large language models to translate, like, human, like, documents with specifications into logical specifications that we need for, like, requirements that we need for formal methods. But beyond that, there is some uses of large language models in SAT solvers, for example, not large language, but neural networks in SAT solvers for guiding, like, which branch to explore first. And people do a lot of interesting research, but I personally try to keep my exposure to neural networks. If I can do it without neural networks, I like to do it without neural networks. But in the artificial pancreas domain, it's being driven by mostly by others in medicine. They want neural networks, and so then I'm interested in getting it done right and exposing the dangers of doing it. I see that as part of my research.
What's the benefit of using a neural network in it? Because it seems like there's so many downsides, and you're trying to predict something that is inherently so unpredictable. Like, why would you want to implement it at all?
Yeah, so that's the point, right? People, I mean, at the end of the day, people with type 1 diabetes want the biggest thing that they want is convenience, right? They want something that's as good as the natural pancreas that got destroyed by some autoimmune process, right? So they don't have access to that anymore, but they want that convenience. They want to be able to eat anything. They want to be able to like go on a run whenever they want. They don't want to have to interact with the pump and say, hey, I'm going on exercise, shut down. And if the consequences of forgetting that means hypoglycemia, they're going to have the seizure right in the middle of their run. Or so people want convenience, right? People want to live lives. I mean, the same pattern is seen in, for example, cardiac devices. There's a group at Stony Brook. They look at very similar what we are doing to artificial pancreas. They are doing to ICDs, like introverter, like these cardiac defibrillators, so that treat like pacemakers and defibrillators, right? And they are looking at, and in fact, we have some work in our lab as well from Ashutosh Trivedi's group for that. And again, the point here is people don't want inappropriate shocks. Like, people don't want to be driving and the device gives them a big shock because it confused some heart rhythm pattern for tachycardia or something, right? So people just want convenience from these things. And so if AI could give them that convenience, they are happy to use that. But then, and neural networks are really convenient. You have a large volume of data. You really don't want to think about anything, like any background information. You throw a network at it, right? It's so convenient, right? That's really what drives a lot of people to use it. But then in a safety critical environment, you really need to ask the difficult questions. Like, even if you get good results, then how do you do that, right? I mean, it's the same for a self-driving car. We had a workshop on self-driving cars at Penn State. And I remember I was super happy at the end because I was gunning throughout the workshop that these things should not be on the road. The reason is, if you think safety is the main reason for self-driving cars, then I can give you 100 reasons why safety is not the reason why you should be using it, right? But, at the end of the day, it's mostly convenience, right? It's mostly labor costs, right? I mean, what drives these changes is a little bit beyond my ken, right? For artificial pancreas, there's a clear clinical use, right? It really improves. It's been really shown to improve people's time in range, all kinds of outcomes for type 1 diabetes. I mean, the clinical rationale for it is beyond question. Now, the interesting thing is how safe can we push all this adaptability? Like it needs to fit hand in glove to your life, right? It needs to be safe, where a doctor just gives it to you and you use it and it stays on for months on an end and no problems, right? That's not happening, right? That's really the part where we are, the whole project is stuck, right? You really want that adaptivity, those intelligent features, but they come at a cost, and the safety needs to be understood.
Would it then involve creating a separate neural network based on each individual's data? Would that also then create massive amounts of, computation you have to do per person and make it, something that's already slightly expensive to do for insulin is known for high costs there. Like, would that also make that even more costly?
No, I don't think so. I mean, part of it is you're hoping that the previous network is already good enough, right? So then you're just tweaking it a little bit. You're probably going to run a few batches, right? Typically, that's how people imagine, right? You get some new data, so you'd run a few more batches of gradient, descent or something like that, right? And just stop there, right? So you're not really going to invest in a full-fledged, like from scratch, let's create a new neural network. But
you can actually train you can fine tune a model based on a fairly small amount of data on your desktop in half an hour.
Absolutely.
Yeah.
Or even on your device, like it could be on your cell phone like device.
Yep.
Yeah. That's part of the problem, right? These things are so convenient and so easy to use and deploy, right? Everything's kind of commoditized right now. The question that I'm really interested in is it safe? And that's the party pooping question. So sorry to use that word, but that's the question that's really like busting the bubble a little bit, right? And that's part of what I really like to do. Ask some of these questions about machine learning, like think about safety and think about how we could make AI safer. I'm not saying AI is a bad thing. I just think there are applications for which it's perfectly okay to do, and there's no safety questions involved. But there are applications for which safety is important. Yeah. Server. Sorry, did I get your name right?
Thank you, Professor, for your. It's okay, totally fine. And first of all, thank you for this talk. I learned some of the keywords from your talk. Probably my target was AI. In the talk, I wanted to ask that what was the AI-based formal verification or something. So at this moment, I want to ask you that for AI-based model, we should focus on only safety, like autonomous driving, as you mentioned, that it's for only safety, like for healthcare, it should be also AI-based safety, because a model could work 80%, 90% based on a testing data set, but it's not full secure. So for AI, we should focus on only safety issue?
No, I mean, yes and no. I think safety is super important in certain applications of AI. I think self-driving cars, safety is super important. You don't realize how safety critical a car is when I don't want to scare you, but you're driving in a metal box that's going at 80 miles per hour. And you're really hoping that those brakes and those steering are available for you to slow you down if you need to slow down, or to steer you away if you need to steer away. And if something takes the control authority away from you, you better want some good assurance. So safety is super important, and for some applications it's more important than others. So the AI that's looking at pictures of pandas and just telling you whether it's a panda or not, or that's classifying pictures on your iCloud and putting them away in different bins, it's not that safety critical. Okay, it put a picture in the wrong place, that's sad, but it's not safety critical. But there are safety critical applications. And some applications, start out as not being safety critical and may easily become safety critical, right? Like an AI that automatically, tries to, let's say you have an AI that starts sending messages to people, and somehow, the person is already depressed, and it sends the wrong kind of message to them and causes them to be like really depressed or have a psychotic episode, right? Those sometimes these chatbots can be very, very safety critical, right? Depending on who's interacting with them, it can really mess them up. So safety is, I think, really, really important for AI. We underappreciate safety until and most of the times, you don't think about safety because it doesn't affect you, right? It doesn't affect me. Like I don't have an artificial pancreas, so, or I'm not like a kind of person who's going to get upset by what the chatbot said, right? But there are people you have to really think about, is it going to be safe and usable for everyone? And often, you want to be careful, and that's a part where when you are working for a company, right, then you have to really say, you can't really ignore people with depression using your chatbot, right? What it would do to them. If you don't know, then it's going to be a liability issue for you, or right. So safety kind of gets to be super important. I don't know that formal methods is the answer for safety. It's a very limited kind of answer for safety, but safety is a bigger issue beyond formal methods, but safety in itself is very, very important.
How do you do the analysis for understanding when you're, what the like cost benefit analysis, right? Because one of the, you could make something absolutely safe, but it might cost an infinite amount of money in order to make it so.
Right.
What's the cost benefit, and how do you,
Yep.
as a practitioner of formal methods, approach delivering that message to your customers?
That's a super interesting question. I mean, it's a little bit beyond my pay grade, but I'll give you an answer anyway. So the point here is, as a researcher, my goal, my job in life is to think about how methods for making software provably safe, right? The cost benefit analysis enters the messy world of legal, right? So I have worked with companies where they will tell me, like in confidence, of course, they will never tell me really. I sign NDAs for a reason. They will tell me, for example, the legal team really looks at, what's the, like, okay, we end up killing a person. How much are we going to have to pay out in damages? They would then make a calculation, and then they would say, how much do we have to spend to make it like this extra bit more reliable? And basically, they are going to draw the line on that, and then they take on the liability, right? When you think about it, it's a really cold calculation, but then they will tell you, look, if we were this anal about every single product, we wouldn't be able to put a product out, right? Every company will tell you that, right? If you are like Toyota wouldn't be able to put a car out on the market if it worried about every single bug. So they just take the liability on, right? So they are just going to do a very cold-hearted calculation like, okay, I'm going to be hit with a 20 million lawsuit by 100 people. So any bug that's going to be less than that severe, 20 million affects 100 people, 20 million per lawsuit, I'm going to take that liability. Fine, forget it. Don't bother fixing it.
Yeah, we do that in the security space, right? Because the only way to have a fully secure system is to turn the system off and throw it in the ocean. And
Absolutely.
but that's often that often belies the benefit that system has. And so where do you draw the line? What's the balance?
Yeah, no, that's the benefit of working in academia. When I worked in industry, I would have some of these conversations with people in the management. But now that I'm in academia, I just don't need to, right? I mean, my job is to educate students and to do research on the mathematics behind this and the applications behind this. And I'm not, at some level, that concern thankfully has been taken out of my hands. So that's one of the blessings of the ivory tower, right? You can do this, and it's one of the reasons I love being in academia. I don't need to worry about how much it costs. To me, it can be as much cost as needed. I'm going to work and try to find a way to make it less expensive. That reminds me, I'm 5 minutes late for my next meeting. I was supposed to go 10 minutes ago. And Sarah, thanks for reminding me.
Thank you very
Okay,
much. I appreciate your time.
Thank you. Yeah, I appreciate it a lot. I know there's some questions. Just email me. I will take it by email. So thanks so much. See you.
No problem. Thank you, Sriram.
Thank you, Professor. Bye.
Bye, everyone.